Let's do this bad boy. And if you can do this one, you can do any of them. So I want you to at least struggle with it and get started. Okay, here's the reaction we want. I would like to know the change in enthalpy for this reaction. What is the change in enthalpy for this reaction? And here are the reactions we are given. So see if you can't take the skills that I just gave you, okay, and think about it. At least think about which reactions we need to use. I'm going to rewrite this on the board while you're thinking about it, and then we'll go over it. All right, folks. Here we go. Hopefully you at least figured out what reaction you want to use first, and you kind of got started with it. So let's talk about this. So I want this, again, we're doing a synthesis reaction. This is actually a hydrogenation of acetylene. So you take organic chemistry, you'll learn about palladium catalyzed hydrogenation reactions of olefins. Just wait, it's going to be a good time. It's going to be a good time. Anyway, we are going to try to figure out the change in enthalpy for this reaction. We want the change in enthalpy for this reaction. How are we going to do that? Well, we're going to use this series of reactions and hopefully combine them such that everything cancels out except for that. So the first thing we need is C2H2. So we need to find the reaction that's got the C2H2 in it, and it is the second one. We need C2H2 on the reactant side. Check. But we got a problem. I only need one C2H2, and there are two of them. So we need to divide this entire reaction. This whole reaction needs to get divided by 2, and then we need to divide the enthalpy by 2. And what does that mean? Well, that means, unfortunately for this guy, an improper fraction. I know, man. Now, if you would rather, operate in decimals, then you do decimals. But I'm not scared of fractions. So I'm going to keep the fractions. You do you. So we need to divide this entire second reaction by 2, because I only want one C2H2, and this one's got 2 of them. So here we go. That's going to be C2H2 plus 5 halves oxygen goes to 2CO2 plus H2O. And then I need to divide this by 2, so that's going to be what, negative 1,200, I don't trust myself. That's what that's going to be. That's going to be negative 1,299.5 kilojoules when we divide that bad boy by 2. So that's the first thing. This reaction is now gone. It's done. It's done. Next up, we need H2. We need 2 of them on the reactant side. So we need to look through these reactions and see which one's got H2. Well, it's the third one. Third one's got it. Okay, it's got 1 H2 on the reactant side, but I need 2. So we need to multiply this entire reaction by 2, which means we need to multiply that enthalpy by 2. So we're going to distribute a 2 into here. That's going to become 2H2 plus 2 times a half is 1, 1O2, and that goes to 2H2O. Then we multiply that by 2, and that's going to be negative 572. Woo! Still got it. The negative delta is negative 572 kilojoules. That reaction is now gone. See you later. Adios. And last but not least, I need C2H6. So I've taken care of that. None of them were in multiple reactions, so that's good. And now I need a C2H6. Now I need one C2H6, and I need it on the product side. So if we take a look in reaction 1, which is all we have left, that C2H6 is on the reactant side. We need to flip that top reaction. So we're going to flip this top reaction. It's going to become 2CO2 plus 3H2O. And that's going to go to C2H6 plus 7 halves oxygen. Since we flipped it, this goes from a negative 1,560 to a positive 1,560. So the change in enthalpy is now a positive 1,560 kilojoules. And now it's time for that Matt Damon Goodwill Hunting moment right here. Okay, this is where you get to cancel out crap that is on both sides of the reaction. I like to do a little squiggly line now through my reactions. arrows, to separate the reactants from the products. And we're looking for crap that's on both sides. So the first thing that jumps out to me would be the two CO2s. I got two CO2s there. I got two CO2s there. They cancel out, right? That jumps out at me. Next would be the three H2Os. Take a look at this. I got two H2Os here and an H2O there. That's three H2Os. I got three H2Os there. The three H2Os cancel out, right? 3 and 3. And now the O2s are a little tricky to see, but you can do this. Trust me, right? I got 7 halves O2 over here. I got 5 halves and 1. I need to add these up, but you can't add them until you find the common denominator. So that's got a 2. 1 is really 2 over 2. 5 halves plus 2 halves is 7 halves. That's 7 halves. All the O2s cancel out. What am I left with? I'm left with C2H2 plus 2H2 goes to C2H6. And now I can just add up those enthalpies. So negative 1,299.5 minus 572 plus a 1560. And we get a change in enthalpy for this reaction of negative 311.5 kilojoules. What does that mean? That means if you did this synthesis reaction, this hydrogenation reaction of this alkyne, this acetylene hydrogenation, it would release energy. It's going to release 311.5 kilojoules of energy per mole of reaction. So for every 1 mole of acetylene that goes in, for every 1 mole of ethane that comes out, and for every 2 moles of H2 that go in, you will release 311.5 kilojoules of energy, because it's a negative number. Woo! I'd like to get the change in enthalpy for this top reaction using these reactions. This one, on a scale of 1 to 10, is like a 2. All right, give this a shot. I'm going to copy it down on the board. So let's talk about this guy. Here's how I would work through this. This is the reaction we want. So the first thing I need is calcium, Ca. If we look, Ca is in the first reactions. In this guy, not in this guy. So we need this. We're going to use the first reaction. Ca plus a half NO2 goes to CaO. And since we didn't do anything, the enthalpy stays a negative 635.1. This was perfect just the way it is. 1 calcium on the reactive side, good to go. That reaction is now done. Now, this reaction actually allowed us to kill 2 birds with 1 stone. Here's what it allowed us to do. It not only took care of the calcium, but it took care of the half of an oxygen. So that's done. I already took care of that. So you got to have a little bit of awareness here of what you did. So that's done. That's done. Now we need CO2. CO2 is in the second reaction, but it's on the wrong side. So on the product side, I need CO2 on the reactant side. So we're going to need to flip the second reaction. And if you're paying attention, that's also going to get my calcium carbonate on the correct side as well, kind of looking ahead. So we need to flip the second reaction. This is going to become CaO plus a CO2 goes to CaCO3. And since we flipped it, the enthalpy now gets changed to a negative 178.3 kilojoules. And now we got, again, it's the Goodwill Hunting moment. Can you cancel anything out? This is not very exciting. We only get to cancel out the calcium oxide. I've got 1 calcium oxide on the right, 1 calcium oxide on the left. They cancel out. What am I left with? I'm left with Ca plus a half an oxygen plus a CO2 goes to a calcium carbonate, CaCO3. That's exactly what we wanted. Since we got what we wanted, we can just add up the enthalpies. So a negative 635.1 minus 178.3 is a negative 813.4 kilojoules. Again, exothermic reaction. Yeah. Cool. Why don't we try another one? Let's keep doing it. Try this guy. We would like to know the change in enthalpy for that reaction using these two known or given reactions. I'll rewrite it. You do it. I'll rewrite it. We need two NOCLs on the reactant side. We look at our given reaction. NOCl is in the second given reaction. But I need it on the reactant side, and I need two of them. Ladies and gentlemen, this is going to be the walking and chewing gum. You got to do two things at once. Okay? We need to flip this reaction, and we need to distribute it too. I know, but you can do this. You can do this. Okay? I need, okay. So 2NOCl goes to 2NO plus a Cl2. So now it's flipped. That becomes positive, and we need to multiply it by 2. So positive 39.6 times 2, that becomes a positive 79.2 kilojoules. That reaction is now dead. So now I need N2. So that took care of it, done. Now I need N2. I need N2 on the product side. N2 is in the first reaction, but it's on the reactant side. So I'm going to have to flip it, and that's only a half an N2. I need one N2. Once again, walking and chewing gum here. We need to flip and multiply by 2. So we're flipping and we're multiplying by 2. You can do this. Here we go. That's going to become 2NO going to an N2 plus an O2. Now, this becomes negative because it was flipped. And we got to multiply that by 2. So that's a negative 180.6 kilojoules. And now, again, not in a very exciting Matt Damon moment here. 2NO gone. And we get what we wanted. 2NOCl goes to N2 plus O2 plus Cl2. Now we can add up that enthalpy. And we get negative 101.4 kilojoules. That reaction, again, exothermic, released 101.4 kilojoules of energy. Let's see if we can find another one, and then maybe we'll take a break, right? It'll be a good, practicing Hess's law is very important. There are going to be some Hess's law problems on the test on Thursday, so we got to get it down, right? Hopefully those were some easier ones. Let's do a tougher one. Yeah. Here we go. That's what I'm talking about. We want this reaction at the top, and we got these three reactions here at the bottom. Give this a shot, folks. You can do it. So let me tell you how this guy works. So again, our goal is to get the change in enthalpy, how hot or cold, how much energy will this absorb or release without actually doing this reaction. So it's kind of cool that we can, and it's a pain. Imagine if you had to do this in real life. Imagine if you were trying to get the change in enthalpy for a reaction you didn't know, and you had to go look up a bunch of reactions and figure out how to get them to combine. Like, I've done the hard part for you. Like, I found these reactions that combine to make that. I hate writing these problems. Like, I like doing them, hate writing them, right? It's like, anyway, enough about me, more about you. Here we go. C2H4. We need C2H4 on the reactant side. Reaction 3 has C2H4 in it, but it's on the wrong side. So we're going to flip reaction 3. So we get C2H4. That goes to 2C plus 2H2. And now this becomes a negative 52.3 kilojoules because we flipped it. And now I need 6 F2s. But here's the thing. F2 is in more than one reaction. So you know what we do? Skip it. Right? So do you see how it's in? Like, we skip it. We do the 2 CF4s next. So I need 2 CF4s. CF4 is in the second reaction, but there's only one of them. It is on the product side. We need to multiply the entire second reaction by 2. So this becomes 2 C's plus 4, plus 4 F2 goes to 2 CF4s. And then we multiply that by 2, and the enthalpy becomes, what is that, negative 1,360? negative 1,360 kilojoules. That reaction is now gone. And now we need 4 HFs. The first reaction has got HF in it, but it's got it on the product side, but there's only 2 of them. So once again, we're going to multiply the first reaction by 2. So this becomes 2H2 plus 2F2 goes to 4HF. We're going to multiply that by 2, and that becomes, oh boy, negative 1,074 kilojoules. Never trust myself, though. So there we go. So now, before I feel confident in adding those up, I want to check my work. Again, Matt Damon moment. Can you get anything to cancel out? So I see 2 H2s on the product side and 2 H2s on the reactant side. I see, let's see, I see 2 carbons on the left and 2 carbons on the right. And these F2s will combine because they're on the same side. So what are we going to be left with? We're going to be left with a C2H4 plus 6F2 goes to 2CF4 plus 4HF. And now we add that up. Here we go. Negative 52.3 minus 1360 minus 1074. That is a change in enthalpy. Once again, exothermic. I think they've all been exothermic. That just doesn't, they can be endothermic. But anyway, we got a total change in enthalpy of negative 2,486.3 kilojoules. How'd we do? How many people got that one right? If you got that right, give me a thumbs up to check in here. There we are. All right. There we go. That's good. That's good. I would say something like this, probably level of difficulty, similar to like the test. This kind of problem is not super hard, right? You got to flip stuff. You got to multiply stuff. You got to it just shows the rules of Hess's law. You got to show all this work, right? Cross the stuff out. It's but hopefully my method here of just working your way across the given reaction, skipping something if it's in more than one, hopefully you kind of see how to do that.